For our next lesson, we're going to dive back into the previous chapter to take a look at local linearity, basically a topic that we began the whole entire year with. If you take a look at our objective, we're going to use the tangent line to approximate values of our function near the point of tangency. And that's an application of local linearity that we didn't use up until this point. As a matter of fact, the way we saw it was basically what's happening in this picture right here. Remember, day one in this class, I showed you this graph right here. Tricked you into thinking that it was a line, and when I zoomed out, it was actually the sine graph, right? It was the idea that whenever you zoom in on a differentiable function, it starts to look more and more like a line, right? And that's basically how we stated it, although at that point we didn't know what the heck differentiable meant. Local linearity is a principle that differentiable functions can be approximated by a line over some small interval. And I can see it happening, right here in this series of pictures right here. Now we have a better perspective of what the heck this differentiable means. We know that our function has to be continuous, first of all. It can't have any sharp turns, and it can't have any vertical tangent lines if we're going to use this local linearity. If you take a look at these next two pictures here, right, if we were to zoom in on this little point here, it looks more and more and more like a line, right? But if it is not differentiable, like that sharp turn, no matter how many times that we zoom in, we can never approximate that function by a line. So when your function is differentiable, it is locally linear, which is fortunate because lines are so easy to work with, and we're going to use that principle and the tangent line to approximate values of the function just really, really close to the point of tangency. Here, let me sketch on this just a little bit here. At this point of tangency, at point A, let's say I draw in a tangent line right there. Of course, the further I get away from this point A right here, then my tangent line doesn't do a very good job of approximating this function, right? But really, really close to A, it does an okay job, and that's what we're going to use it for. All right, so let's take a look at this first example. Let y equals f of x be differentiable at x equals A. Write the equation of the tangent line at x is equal to A. This is going to be the easiest question that we have done all year. What two pieces of information, please tell me, do you need in order to write the equation of a line? Well, we need two things. We need point and we need a slope. Well, the point is half given to us. It's a comma, and then the y value would just be f of a. And then the slope, well, if I have this function, I get its slope by taking the derivative. So y prime is equal to f prime of x, but we want that specifically. This is all the slopes, of course. All the slopes. We want it only at a, so its slope is going to be specifically f prime of a, right? That's just some sort of number. And then we're going to put both of these things together in order to write the equation of the tangent line at x is equal to a in point slope form, because it's our friend. So we have y minus the y value, f of a, is equal to our slope, f prime of a, times x minus our x value, which is a. And you can leave it like that, but sometimes we just see it, especially if we're going to use it to approximate the value of a function. We usually write it with this f of a marched over to the other side, and by marched I mean added. So f of a plus f prime of a times x minus a. Voila, we're back in Algebra 1 again. Okay, so hey, let's come back over here so we can see this all nice and animated. Here's our point, here's our slope, and then here's the equation of our tangent line. So this is our linear approximation. If y is equal to f of x is a differentiable function at x is equal to a, then the equation of the tangent line at x is equal to a is, as we just saw it, y is equal to f of a plus f prime of a, there's our slope, times x minus a. And the linear approximation of our function is what you see right there in purple. Notice that it says our function is approximately equal to, and then that's the linear equation right here. It's the equation of the tangent line. But this only is approximately equal, really close, super close to our point of tangency, x is equal to a. All right, another word on here is linearization. If you can say that, probably better than I do. It just is the process of turning your function into a straight line because they're so much easier to work with. So we're saying that the linearization of our function is just equal to that tangent line at x is equal to a. So let me give you a preview of what's to come here. We have ourselves, let's say, some sort of function that is graphed. Who knows what this function looks like, but it's probably graphed in purple. Okay, so let's say that, dang it, let's say right about here, I want to approximate this function. So I am going to zoom in, zoom in, zoom in, zoom in order to find the equation of the tangent line at this particular point. Let's call this one a, and of course our function is f of x. Okay, so what I would want to do is use the equation to get some sort of value that's just like right over here in order to approximate the value of the function. We're just going to plug this value in here, whatever it is. Maybe it's b. We plug that into, instead of the function, which is harder to work with, if not impossible to get an actual answer from, we'll plug it into the tangent line, which is super easy to work with.